Section 5.3, properties of the trigonometric functions. In section 5.2, the following definitions were given when theta is an angle in standard position with its vertex at the origin, and point P has coordinates x, y is a point on the unit circle whose radius is 1. That corresponds to an angle of theta in radians. The sine of theta is equal to y, and we can think of this as y divided by 1, where y is the length of the side opposite the angle theta, and 1 is the length of the hypotenuse, which is the radius, which is 1. So this ratio is the ratio of the length of the side opposite. So this is O for opposite, and 1 is the length of the radius, which is the hypotenuse of a right triangle. So the memory device or mnemonic SOH is to remember the sine ratio is the length of the side opposite the angle divided by the hypotenuse length. The cosine of theta equals x, and x is divided by 1. X is the length of the side adjacent, so the A stands for side adjacent to angle theta, and 1 is the length of the radius, which is 1, which is the hypotenuse of the right triangle. So to remember this, we have C for cosine is the ratio of length of the side adjacent divided by the hypotenuse. And tangent of theta is the ratio of y to x, where the denominator x cannot be 0. And this can be remembered as the tangent of an angle theta is the ratio of the length of the side opposite, so this is O for opposite, divided by the length of the side adjacent. To remember this definition of tangent, we can use T for tangent is the ratio of the length of the side opposite divided by length of the side adjacent to angle theta. So this memory device or mnemonic SOHCAHTOA is to help remember the definitions of sine, cosine, and tangent. The cosecant of theta is the reciprocal of the sine of theta is 1 divided by y, where y cannot equal 0. Secant of theta is the reciprocal of the cosine of theta is 1 divided by x, and thus x cannot equal 0. Cotangent of theta is the reciprocal of the tangent of theta, and thus is x divided by y. Y cannot equal 0. So we should pause for a minute and think about for what angles is x equal to 0. X is equal to 0 for angles that terminate on the y-axis. So angles like pi over 2 have an x coordinate of 0. 3 pi over 2, likewise, x is 0. And for y equals 0, that occurs for angles that terminate on the x-axis, either the negative portion of the x-axis or the positive portion of the x-axis. The y-coordinate is 0. Use these definitions above to make conclusions about the domain and range of the following functions. To begin, make sure you're clear on what variable is the domain or the input and what variable or variables are the range, the output values. For the sine of theta, the input is theta, which is a real number, negative, 0, or positive, and the output is equal to y. So we can express this as y is sine of theta. This means that the domain of the sine function is the set of all real numbers, and the range is -1 to +1. So to justify, we can think of the unit circle and visualize how the y values vary between 0 to +1 to -1. So we can express it this way. Y is greater than or equal to -1, and y is less than or equal to +1. This is equivalent to stating the sine of theta is between -1 and +1, expressed as an absolute value. The absolute value of the sine of theta is less than or equal to +1. For the cosine of theta, the input is the angle theta, and the output is y. Or we can say that y is the cosine of theta. The domain of the cosine function is such that theta can be any real number, -0, positive, no restrictions. And the range, like the sine function, the cosine of theta is between -1 and +1, because as theta is a variable that changes, as theta changes, the value of x, or the cosine of theta, is between -1 and +1. This can be expressed as the absolute value of the cosine of theta is less than or equal to 1. For the tangent of theta, the input is any angle theta that does not produce division by 0, and the output is y. Y is equal to the tangent of theta. The domain of the tangent function is all real numbers for angle theta, except odd integer multiples of pi/2. And the range is all real numbers. So the reasons are, if the tangent of theta is equal to y divided by x, which is equal to the sine of theta divided by the cosine of theta, then the angle theta can be any real number except any angle for which the cosine of theta equals 0. And that occurs on the y-axis for angles like pi/2 or -pi/2, 3pi/2, -3pi/2. So we have to restrict theta from being angles such as +1pi/2, -pi/2. So we say that plus or minus 1 is an odd integer multiple of pi/2. And if we quickly draw a unit circle here and think about angles that terminate on the y-axis, we'll have x coordinates of 0. Other angles for which this happens are positive 3 pi over 2 or 3 times pi over 2. That's 1.5 pi. Going clockwise, negative 3 pi over 2 will have an x coordinate of 0. And likewise, if we go counterclockwise, 2.5 pi, which would be 5 pi over 2, 5 times pi over 2 is also called an odd integer multiple of pi over 2. And similarly, negative 5 pi over 2 corresponds to a point on the y-axis for which the x coordinate is 0. And we'll put ellipses here because there are going to be infinitely many angles for which x equals 0. For the cotangent of theta, the input is angle theta, any real number, and the output is going to be y equals the cotangent of theta. The cotangent of theta is the reciprocal of the tangent of theta. Tangent of theta is y over x, so the cotangent is x divided by y. And thus y cannot equal 0. So the domain of the cotangent function is any real number, theta, so long as the angle theta does not correspond to a point where y does equal 0. So we're going to need to exclude certain angles theta. And the restrictions on theta are going to be integer multiples of pi over 2. So for example, 0 radians corresponds to a point where y equals 0, and 0 radians is also expressed as 0 times pi, so that is an integer multiple of pi. Positive 1 pi is an angle where that corresponds to a point on the x-axis, and y will equal 0. Clockwise, negative pi also corresponds to a point giving y equals 0. And similarly, plus 2 pi and negative 2 pi are angles that correspond to points on the x-axis or the horizontal axis, which give a y coordinate of 0. And this repeats indefinitely, and these angles are called integer multiples of pi. Now remember that the set of integers is the set Z, and if k is an integer, k is an element of the set of integers, the set Z, then we want to restrict theta for the cotangent function and have theta not be an integer multiple of pi, or k times pi. Now, the range is going to cover all real numbers, since the ratio of x over y is also the ratio of the cosine of theta divided by the sine of theta. So the cotangent function cotan of theta is cosine of theta divided by the sine of theta. The sine of theta in the denominator varies between -1 and +1 and includes values very close to 0 in the denominator. When the denominator values are very small, close to 0 and positive, the ratio will go to positive infinity. When the denominator value is very small and negative and close to 0, this ratio will go to negative infinity, assuming that the numerator value is positive. And thus, all real numbers will be covered in the direction of y. That is, the range is the set of all real numbers. The same is true for the tangent function. So the range of the tangent of theta, which equals y, will cover all real numbers, since the denominator cosine theta for the tangent function varies between -1 to +1, which includes 0 and small positive numbers and small negative numbers. The tangent of theta will cover in the y direction all real numbers. For the cosecant of theta, the input is any angle theta that does not produce division by 0, and the output will be the cosecant of theta is less than or equal to -1, or cosecant of theta is greater than or equal to +1. The domain of the cosecant function is all real numbers except integer multiples of pi. That is, we have to restrict certain angles which will produce division by 0. The range is all real numbers greater than or equal to 1 or less than or equal to -1. Justify the domain. So since the cosecant of theta is equal to y, and cosecant of theta is the reciprocal of the sine of theta, we must restrict theta from being any angle where the sine of the angle is 0. And this occurs on the horizontal axis. So picture the unit circle, and y is 0 for any angle that terminates on the x-axis. So we have to not allow 0 pi or 0 radians, plus 1 pi, minus 1 pi, plus 2 pi, minus 3 pi. So theta cannot be any angle that is an integer multiple of pi, k times pi. Now, in terms of the range, the greatest that sine of theta can be is 1. So if y equals the sine of theta divided into 1, or 1 divided by sine theta, when sine of theta is 1, on the positive side, 1 divided by 1 will be 1. And when sine of theta is less than 1 and getting smaller and approaching 0, the values will go to positive infinity. So the range on the positive side is going to equal 1 when sine of theta is 1, and will be greater than 1 when the sine of theta is small and close to 0. So let's think about this on the unit circle. Now there are going to be certain angles where the sine value is very small and positive. So angles that are close to 0 will be such that the sine of theta is small and positive. And the closer we are to 0 radians, the smaller will be the sine of theta. And 1 divided by sine theta will be 1 divided by a small positive value will go to infinity. In quadrant 2, for angles that are close to pi, the sine of the angle will be very small and positive, and the closer we get to pi radians, 1 divided by the sine of theta will have a limit of positive infinity. Now, the other part of the range is y will be equal to -1 when the sine of theta equals -1, and will be less than -1 when the sine value is small and negative. So for example, in quadrant 3, when the angle is a little more than pi, we call that pi plus. The y value, or the sine of the angle, will be small and negative because the angle terminates in quadrant 3. So the closer is the angle terminating in quadrant 3 at an angle of pi plus, a little more than pi, the sine of theta will be very small and negative, so the cosecant will be +1 divided by the sine of theta will go to negative infinity. And the y values will get very large negative and be much, much less than -1. Similarly, in quadrant 4, the closer we get going counterclockwise to 2 pi radians, the y value will be shrinking to 0 and will be negative, very small and negative. So the angle that's close to 2 pi but less than 2 pi is 2 pi negative. And the closer we get to pi in quadrant 4, y will get increasingly larger, negative, and go to negative infinity. So the range will be all real numbers greater than or equal to 1, union all real numbers less than or equal to -1. For the secant of theta, the input is angle theta, a real number, and the output is, in the range, secant of theta is less than or equal to -1, or secant of theta is greater than or equal to +1. Now for the domain, let's write the definition of secant of theta. Secant of theta is the reciprocal of the cosine of theta, and cosine of theta corresponds to x. So the domain is a set of allowable input values for theta with restrictions on any angle that makes x equal to 0 because x is in the denominator. So since we cannot have x be a divisor of 0, x cannot be 0, we cannot allow x to correspond to any angle theta that terminates on the y-axis, because then that will correspond to a point whose x-coordinate is 0. So for the domain, the restriction on the input theta cannot be any odd integer multiple of pi over 2. So positive or negative, pi over 2, positive or negative 3, pi over 2, and there will be infinitely many more angle restrictions on theta. Now the range is the set of output values, is the set of values for 1 divided by the cosine of theta. The greatest that cosine of theta will be is 1. The maximum value of the cosine of theta is 1. So the secant of theta will equal 1 divided by 1 when the cosine of theta equals 1. So on the positive side, that will be the minimum value. And then when cosine theta is very small and positive, let's visualize when is that occurring. So on the unit circle, cosine of theta, which is the x distance, is very small and positive when the angle is very close to pi over 2. And the closer we get to pi over 2, the smaller x get, and it's small and positive. So the secant of theta will go to positive infinity as the angle theta gets closer to pi over 2. The other situation is when an angle is increasing, going counterclockwise, and then when we go past 3 pi over 2, just past 3 pi over 2 or 3 pi over 2 plus, x, or the cosine of theta, is very small positive, so the secant of theta is 1 divided by very small positive goes to positive infinity. And therefore, the secant of theta is going to be greater than or equal to 1. Now, on the negative side, the minimum value of cosine theta is negative 1. So since the minimum value of the cosine of theta is negative 1, and the secant of theta is 1 divided by cosine theta, for angles where the cosine of theta is negative 1 gives you positive 1 in the numerator divided by negative 1 equals negative 1. Therefore, on the negative side, the secant of theta is going to be, for some angles, negative 1, and then increasingly negative when the cosine of theta gets smaller and is negative. Because then we have secant theta is positive 1 divided by small negative values goes to negative infinity. So this occurs small negative x values for angles that terminate just past, let's go like this, just past pi over 2 or pi over 2 plus. Because then x is small and negative in quadrant 2. And the closer we are to pi over 2 plus in quadrant 2, the secant will be positive 1 divided by a very small negative value goes to negative infinity. And this also occurs for angles that are approaching 3 pi over 2, getting very close. And the closer we get to 3 pi over 2, which is an angle of 3 pi over 2 negative, the smaller is x, or the cosine of theta. And so the ratio of positive 1 divided by very small negative goes to negative infinity. So the range for secant of theta is greater than or equal to 1, or secant of theta is less than or equal to negative 1. From section 5.2, it was found that the sine of 5 pi is equal to the sine of pi is equal to 0. And to picture this visually, let's draw again the xy axes and think about an angle of 5 pi. Well, 2 pi will be 1 full revolution. 4 pi will be another full revolution. And then 1 pi more, the angle will terminate on the x-axis and correspond to a point whose y-coordinate is 0, and thus the sine value will be 0. And in the last section, it was explained this way, that 5 pi can be thought of as 2 full revolutions around the unit circle, so twice 2 pi radians. That will be 4 pi radians. And we have to go 1 semicircle further, so 1 pi further, to have a sum of 5 pi. And thus the sine of 5 pi will be the same as determining the sine of pi, since both angles terminate on the negative side of the x-axis, and their sine function value will be 0. So in general, the sine of an angle pi, the sine of an angle theta plus integer multiples of 2 pi. That means from an angle theta, if we add 2 pi radians and go around the unit circle 1 full revolution, the new angle, theta plus 2 pi, will have the same sine function value. And the same is true if we go from theta, go clockwise, or subtract 2 pi radians, the angle will terminate and correspond to a point that will have the same sine function value. And therefore, the sine of theta plus 2 pi k is the same as the sine of theta plus 360 degrees multiplied by k times k. And the sine function value will repeat and be the same as the sine of theta. So let's look at an example here. So we know that for pi over 4, or 45 degrees, the sine of 45 degrees, or the sine of pi over 4, is square root of 2 over 2. For pi over 4 radians, which is 45 degrees, the cosine is square root of 2 over 2, and the sine is the same. Now, from this angle of pi over 4 radians, or 45 degrees, if we add an angle of 2 pi and continue going around one full revolution, adding 2 pi, that will correspond to a point that has the same sine value. Or if from angle theta we go minus 2 pi, go clockwise, subtract 2 pi, and terminate, that determines a point whose y-coordinate or sine value is the same. The function values repeat every 2 pi radians for the sine function, or every 360 degrees. The same is true for the cosine function. The cosine of theta will be the same as the cosine of theta plus integer multiples of 2 pi, which means we can add 2 pi times 1, or subtract 2 pi, which is 2 pi times negative 1, or add 4 pi, which is 2 pi times 2, or subtract 4 pi and go clockwise 2 full revolutions. That would be 2 pi times negative 2. Or if you work it in degrees, the cosine of theta is the same as the cosine of theta plus integer multiples of 360 degrees, or 360 times k. Functions that exhibit this kind of behavior, where you can add or subtract something to the angle measure and the values of the sine and cosine functions remain the same, equal, or unchanged, are called periodic functions. And in general are defined as following. A function f is called periodic if there is a positive number p, such that whenever theta is in the domain of the function, so is theta plus p in the domain. And in other words, it's not a restricted value. And the function evaluated for theta plus p is the same function value as the function evaluated at theta. So f of theta is the same as f of theta plus p. If there is a smallest such number p, this smallest value is called the period of the function. Based on this, complete the following statements for both radians and degrees. The period of the sine function is 2 pi radians, which means every time we add an integer multiple of 2 pi radians, the sine function value is the same and it repeats. Or we can say that the period of the sine function is 360 degrees. Every time we add or subtract integer multiples of 360 degrees, we have an angle that corresponds to a point such that the sine function value is the same. Next page. The period of the cosine function is also 2 pi, since every time from a given angle theta, if we add 2 pi radians and go one full revolution, or subtract 2 pi radians and go clockwise, the angle will coincide and terminate such that the point, which has coordinates x and y, will have the same cosine function value. And whether we work in radians or degrees, the period of the cosine function is 360 degrees. Now, the tangent function is a little different, and let's go to the unit circle and discuss why the fundamental period of the tangent function is pi radians. Now we know that at pi over 4, sine and cosine are equal. They're both square root of 2 over 2. And we also know the definition of the tangent function is the sine of the angle divided by the cosine of the angle. So sine divided by cosine is going to be square root of 2 over 2 divided by square root of 2 over 2, which is 1. So as an example, to show that the tangent function's period is pi radians, let's work on the tangent of pi over 4, which is y over x, or sine of pi over 4 divided by cosine of pi over 4. Well, these two values are equal, square root of 2 over 2. So the ratio is going to be equal to positive 1. Now, if we add to pi, the angle that corresponds will have the same sine and cosine values, and thus we could say that the period of the tangent function is 2 pi. However, there's a smaller positive value p, 1 pi, where the function value is going to repeat. If we think about adding pi radians, which is 180 degrees, and we have a semicircle formed, then we're in quadrant 3. The sine is negative, the cosine is negative, and they're both negative square root of 2 over 2. So by adding pi radians, we now have an angle of 1 1/4 pi, or 5 pi over 4. And that's going to equal the ratio of the sine of 5 pi over 4, which will be negative square root of 2 over 2. And the cosine in quadrant 3 is negative square root of 2 over 2. And the function value is positive 1 again. So there's a smaller positive value p of pi radians for which the tangent function repeats. And we could say that the tangent function also repeats at 2 pi radians, but since there's a smaller value, positive value p of pi radians, we say that the period of the tangent function is pi radians, which is 180 degrees. Since the cosecant function comes from the sine function, it has the same period of 2 pi radians, or 360 degrees. Similarly, the secant function and cosine functions have the same period of 2 pi, and the cotangent and the tangent function have the same period of pi. So the period of cosecant, like the sine function, is 2 pi radians. The period of the secant function, like the cosine function, is also 2 pi. The period of the cotangent function, like the tangent function, is pi radians. Use the fact that trig functions are periodic. That means their function values repeat with the fundamental period p to find the exact value of each trig term. Do not use a calculator. The sine of 390 degrees, we'll think of that as the sine of 30 degrees. And 30 is from taking 390 and subtracting 360. So from 30 degrees, if we add 360 degrees, which is one full revolution, that angle of 390 degrees will have the same sine function value as the sine of 30 degrees, since the period of the sine function is 2 pi radians or 360 degrees. So the sine of 390 will be the same as the sine of 30 degrees, which you have memorized and is 1/2. Part B, the tangent of 19/4 pi. Keep in mind that the fundamental period of the tangent function is pi radians. And since 19/4 is an improper fraction, we can think of changing 19/4 into a mixed number, 4 3/4 times pi. So 19/4 is 4 3/4, which you get by dividing 4 into 19 times pi, or 4 3/4 pi. Now 4 3/4 is the same as 3/4 pi plus 4 pi. So 4 3/4, remember and means addition, means 3/4 pi plus 4 pi. That's 4 3/4 pi. Well, adding 4 pi is like adding 2 full revolutions to the angle 3/4 pi. And 3/4 pi is special because 3/4 pi is a multiple of pi over 4. And for pi over 4, cosine and sine have the same value, square root of 2 over 2. So their ratio of y to x, sine divided by cosine, is going to equal 1. But for 3/4 pi, keep in mind this is in quadrant 2, where x is negative and y is positive. So let's just review here real quick. 3/4 pi is an angle that terminates in quadrant 2. And since the cosine is negative and the sine is positive, we have for 3 pi over 4, a multiple of pi over 4, negative square root of 2 over 2, and positive square root of 2 over 2. And since tangent is the ratio of y over x, or sine divided by cosine, their ratio is -1. So the tangent of 3/4 pi, add 4 pi, which is 2 times 2 pi, which is adding 2 full revolutions counterclockwise, is the same function value as the tangent of 3 pi over 4. And the tangent of 3 pi over 4 is -1. Exploration 3, determining the signs of the trigonometric functions in a given quadrant. From algebra courses, you know that the coordinate plane is divided up into 4 quadrants, and they go counterclockwise. So upper right is quadrant 1. Where all points in the plane have a positive x coordinate and a positive y coordinate. In quadrant 2, all points have negative x coordinates and positive y coordinates. So negative, comma, positive. In quadrant 3, all points have negative x coordinates and negative y coordinates. So both coordinates are negative. And in quadrant 4, x is positive and y is negative. Complete the graphs below with the appropriate signs of each of the ordered pairs. The first graph has been given for you. Next page. The sine and cosecant functions. The sine of theta equals y, and the cosecant of theta is the reciprocal value 1 divided by y. So looking at the graph, wherever y is positive, the sine and cosecant functions will be both positive. Likewise, wherever y is negative, the sine and the cosecant functions will be negative. For the cosine and secant functions, since the secant of an angle theta is the reciprocal value, positive 1 divided by the cosine of theta, since x is positive in quadrant 1 and quadrant 4, the secant function value will also be positive. But where the cosine is negative, where x is negative in quadrants 2 and 3, then the secant function will also be negative. Now, since the tangent of an angle theta is the ratio of y to x, or the sine of theta, divided by the cosine of theta, where x and y, or cosine and sine, have the same SIGN, both positive or both negative, the tangent will be positive in quadrant 1 and in quadrant 3, where x and y are both negative. And the ratio of two negatives is positive. In quadrants 2 and 4, where x and y have opposite signs, then the tangent and cotangent both will be negative. So just to refresh and repeat, the cotangent of an angle is x over y, or cosine of theta divided by sine of theta. Name a quadrant in which the angle theta lies if sine of theta is positive and the cosine of theta is negative. So sine of theta is positive in quadrants 1 and 2. Cosine of theta is negative in quadrants 2 and 3. So where there's overlap, that's where the and condition is satisfied, and thus it is quadrant 2. Find the values of the trig functions using identities. Based on the earlier definition of the 6 trigonometric functions, we can now establish the following trigonometric fundamental identities. The reciprocal identities: cosecant of theta is the reciprocal of sine theta. Keep in mind the restriction on theta. Theta cannot be any angle that produces a sine of theta equaling 0. And that occurs on the x-axis. Secant of theta is the reciprocal value of the cosine of theta, and we have to restrict theta from being any angle that terminates on the y-axis and would give the cosine of theta equal to 0. Cotangent of theta is the reciprocal of the tangent of theta, and we have to avoid any angle for which the tangent of theta would give 0. The quotient identities are the tangent of theta is the ratio of sine theta divided by cosine theta, and we have to restrict theta from being any angle that would give the cosine of theta being 0. And again, that occurs for angles that terminate on the y-axis. The cotangent of theta is the quotient cosine theta divided by sine theta to avoid division by 0 and the cotangent function being undefined. The sine of theta cannot equal 0, which occurs on the x-axis. Example 3. Given the sine of theta is square root of 10 divided by 10, the cosine of theta is 3 square root of 10 divided by 10. Find the value of the tangent of theta, secant of theta, and cosecant of theta. So starting with the tangent of theta, which is the sine of theta divided by cosine of theta, just substitute the given value. Sine of theta is square root of 10 divided by 10 divided by cosine theta, which is 3 square root of 10 divided by 10, multiplied by the reciprocal. So this gives square root of 10 over 10 times 10 over 3 square root of 10. Divide and cancel. 10 divided by 10, square root of 10 divided by square root of 10. Final answer, 1/3. Secant of theta is the reciprocal of the cosine of theta. The reciprocal of the cosine of theta is going to be 10 divided by 3 square root of 10, just substituting the given value. Next, you would have to rationalize the denominator and multiply by square root of 10 divided by square root of 10. So that will give 10 square root of 10 divided by 3 times 10, which is 30. And then 10/30 simplifies to 1/3. So final answer, square root of 10 divided by 3. Part 3, cosecant of theta is the reciprocal value of the sine of theta. So substituting for sine of theta is square root of 10 over 10, and bringing that to this denominator, the reciprocal value will be 10 divided by the square root of 10. Rationalize the denominator, multiply by a form of 1 square root of 10 over square root of 10, which equals 10 square root of 10 divided by 10, which equals the square root of 10. Example 4, find the values of the trigonometric functions using identities. Find the exact value of each expression. do not use a calculator. Now, 1 divided by cosecant squared of 35 degrees can also be written as 1 divided by the square of the cosecant of 35 degrees. So cosecant of 35 degrees, quantity squared, is an equivalent way to write that, plus cosine squared 35 degrees now 1 divided by cosecant of 35 degrees quantity squared can also be written in the following way. 1 divided by cosecant of 35 degrees whole fraction squared, because squaring the numerator of 1 gives 1, and then squaring the denominator gives cosecant 35 degrees squared, plus cosine squared of 35 degrees. Now, 1 divided by cosecant of 35 degrees is the reciprocal value of the sine of 35 degrees. So this gives sine of 35 degrees quantity squared plus cosine squared of 35 degrees. Now, the square of sine of 35 degrees is the same as sine squared of 35 degrees plus the cosine squared of 35 degrees. So this is y squared, since the sine of an angle is y. Sine squared is y squared, and since cosine of an angle is x, cosine squared is x squared. So think of this as y squared plus x squared, which is equal to 1. Final answer. Part B. The fraction cosine pi over 3 divided by sine of pi over 3 is equivalent to cotangent, because cotangent is x over y, or cosine of an angle divided by sine of the same angle. So this is cotangent of the common argument, pi over 3, subtract itself, cotangent of pi over 3. And any number subtract itself is equal to 0. Next, the Pythagorean trig identity. Pythagorean trig identity. Using the idea of the equation of a circle, x squared plus y squared equals radius squared, a new identity can be established that will provide another way of solving example 4. Before we go on, let's pause here and draw the unit circle. So an angle theta, let's say it terminates in quadrant 1, determines a point P whose coordinates are x and y, and the radius is r. When we draw the altitude perpendicular, that determines a right angle, a length x, and a vertical length of y, legs on a right triangle, and by the Pythagorean equation, x squared plus y squared equals radius squared. Radius is the hypotenuse. If we divide both sides by radius squared, we get, in the second line here, x squared divided by r squared plus y squared divided by r squared equals r squared divided by r squared. So in the third line, we get the square of x divided by r plus the square of y divided by r equals 1. Well, x divided by r is the definition of the cosine of an angle, theta. So it's the square of the cosine of theta plus the square of y divided by r. Well, y divided by r, by definition, is the sine of angle theta. So we get the square of the sine of theta equals 1. And since addition is commutative, we can change that into the square of sine theta plus the cosine of theta equals 1. Let's label that step 5 and step 6. The square of sine theta is the same as sine squared theta plus cosine squared theta equals 1. The last equation is the Pythagorean trig identity. Sine squared theta plus cosine squared theta equals 1, or that's the same as cosine squared theta plus sine squared theta is equal to 1. Again, this is called the Pythagorean trig identity. Variations of this trig identity are found by starting with sine squared theta plus cosine squared theta equals 1, and then doing the following step. To change sine squared theta into 1, we'll divide by sine squared theta. Divide every term by sine squared theta. So sine squared theta divided by itself will equal 1. Plus cosine squared theta divided by the same value, sine squared theta, equals 1 divided by sine squared theta. Well, since cosine over sine is cotangent, the second term, cosine squared theta divided by sine squared theta, is going to be cotangent squared theta. And since 1 divided by sine theta is cosecant of theta, 1 divided by sine squared theta gives cosecant squared theta. So this is a new identity, 1 plus cotangent squared theta equals cosecant squared theta, which comes from the Pythagorean trig identity. In a similar way, if we start with the Pythagorean trig identity and divide every term by cosine squared theta, we have sine squared theta divided by cosine squared theta. And since the tangent of theta is sine theta divided by cosine theta, we get tangent squared theta. plus cosine squared theta divided by itself, cosine squared theta, is equal to 1. And the right-hand side, 1 divided by cosine squared theta. Since 1 divided by cosine is secant theta, 1 divided by cosine squared theta is secant squared theta. So that's a new trig identity. Tangent squared theta plus 1 equals secant squared theta. Example 5. Find the exact value of a trig function given one of the functions and the quadrant of the angle. Given sine of theta is negative 2/3 and theta is greater than pi and theta is less than 3 pi over 2. Theta terminates in quadrant 3. Theta lies in quadrant 3. Find the exact value of the cosine of theta and the tangent of theta. So two methods or two options using a circle. Let's start with the XY coordinate plane. And let's draw a circle. Where the sine of theta is negative 2/3. Now, since the angle terminates in quadrant 3 and y is negative, and because the sine of theta is the ratio of the side opposite O divided by the hypotenuse h, which is 3, and hypotenuse is the radius of a reference right triangle. That means that the negative goes with length of the side opposite. So the negative on negative 2/3 goes with 2 in the numerator. So theta is an angle that terminates in quadrant 3. And we want to draw a triangle where the radius of 3 in proportion to y is 3 to 2. Radius 3, y is 2. So we don't want y to be short or y to be too long, so to speak. So roughly maybe here, just as an approximation. So here's the hypotenuse of 3 or the radius r of 3 determined by an angle theta that terminates in quadrant 3. So drawing the altitude perpendicular, that determines this right angle, determines a length of y, vertical leg, and a length x. So we have y in length is 2. The coordinate of point P would have a negative y coordinate and a negative x coordinate. So now we can solve for x, and we're going to need x because to answer cosine of angle theta, let's label theta over here on the diagram. Cosine of theta is the ratio of the length of the side adjacent to the hypotenuse. So in reference to theta, theta is going to be the angle such that 2 is opposite. That means that our theta is going to be the central angle whose sides are on the negative x-axis and the radius. So theta will be right in here. So to find the cosine, we need to find x, because that's the side adjacent to angle theta, and the hypotenuse is the radius is 3. So to find x, we're going to apply the Pythagorean equation, and x squared plus y squared equals radius squared. So x squared y in length is positive as a coordinate in quadrant 3, y is negative. It won't matter because you're squaring a negative value. And the radius is the hypotenuse is 3 squared. So solving for x, we have x squared plus 4 is equal to 9. So x squared equals 5 has two solutions, but x as a length is positive, x as a coordinate in quadrant 3 is negative. The cosine value will be negative. So although x has two solutions, positive or negative, square root of 5, because we take the square root of both sides, we get positive, negative, square root of 5. So finally, the cosine of the reference angle theta, again, whose sides are on the negative x-axis and the radius, it's going to be a negative value because the angle terminates in quadrant 3. Is going to be negative side adjacent, which is x, which is negative square root of 5. And the hypotenuse is the radius, which is 3. So that's our cosine value. Now, using identities, we can use the Pythagorean trig identity, which is x squared plus y squared equals 1. X is to be determined. Let's back up a little bit. The Pythagorean trig identity is cosine squared theta plus sine squared theta is equal to 1. Now we were given the sine of theta is negative 2/3. So we can solve for the cosine of theta. First we have cosine squared theta plus sine squared theta is the square of the sine of theta. Let's write it like this first. The square of sine theta, that equals 1. And then substitute for sine of theta, which is negative 2/3. So we have the square of negative 2/3. Quantity squared equals 1. So cosine squared theta plus 4/9. And since we have ninths, let's change the 1 into 9/9 in order to subtract 4/9 from 9/9. So we have cosine squared theta is 5/9. Cosine squared has a coefficient of 1, so we'll take the square root of both sides. This is the square root property. So the cosine of theta is positive in quadrants 1 and 4, but negative in quadrants 2 and 3. Square root of 5. Denominator is square root of 9, which is 3. So in quadrant 3, where x and cosine are negative, the cosine of theta is negative square root of 5 divided by 3, which is the same answer that we got earlier, top right corner. Now, part 2 is to find the tangent of theta. Now, the tangent of theta, by definition, is the ratio of sine of theta divided by cosine of theta. And in quadrant 3, where x and y are negative, the ratio of sine to cosine will be a positive. Now, sine of theta was given as negative 2/3. The cosine of theta we figured out is negative square root of 5 divided by 3. So we'll multiply by the reciprocal. Multiply negative 2/3 times 3 divided by negative square root of 5. So the tangent of theta is positive 2 divided by the square root of 5. Since the 3's dividing canceled, then rationalizing the denominator, multiply by square root of 5 divided by square root of 5. And that gives 2 square root of 5 divided by 5. Now, using a identity, the earlier identity above is tan squared theta plus 1 is equal to secant squared theta. So by using the above identity, tangent squared theta plus 1 is equal to the secant squared theta. And remember, secant of theta is the reciprocal of the cosine of theta, which we know is negative square root of 5 over 3. So to solve for tangent of theta, let's subtract 1 first. So tan squared theta is secant squared theta, subtract 1. Now secant squared is the square of the reciprocal of the cosine of theta. So 1 divided by cosine of theta minus 1. Now 1 divided by cosine theta is at the top of the screen, negative square root of 5 over 3. So that's going to give the square of 3 divided by negative square root of 5, quantity squared minus 1, which is equal to 3 squared is 9. The denominator squared is positive 5. And since that fraction is fifths and 1 is 5/5, we have 9/5 subtract 5/5, which is 4/5. Therefore, we have tangent squared, but we don't want tangent squared, we want tangent. So we have to take the square root of both sides, and this tangent squared has a coefficient of 1, which is a good thing for applying the square root property. So we have 1 tangent squared theta, and we'll take the square root of that left side, and that equals 4/5. And we'll take the square root of the right side. So there's two solutions, positive or negative, depending on which quadrant you're in. Square root of 4 is 2, divided by the square root of 5. And then, as we did earlier, rationalize the denominator, which we did over here. Multiply by square root of 5 over square root of 5. And since we're in quadrant 3, where x is negative, y is negative, the ratio of y to x is positive. So again, in quadrant 3, the tangent function value is positive, and the tangent of the angle is 2 square root of 5 divided by 5, which is the same answer we got over here, 2 square root of 5 over 5, positive. Recall from earlier chapter that a function is even if f of negative x is the same as f of x. And the graph would have y-axis symmetry. And a function is odd, recall this definition, if f of negative x is the opposite of f of x. Now with trig functions, the input x is going to be an angle theta in radians. What types of functions are the sine and cosine functions, odd or even? Use the unit circle graph on the right to determine which is an even function and which is odd, using theta as the input for x. So looking at this picture, this graph here, angle theta terminates in quadrant 1, determines a point P. Let's draw the altitude. That is the length y or distance y, so the sine value is some positive value, because point P lies in quadrant 1 and the y coordinate is positive. Now, negative theta is an angle that is clockwise and will determine point Q in quadrant 4, where y is negative. And when we draw the altitude, the perpendicular here, that determines this length y, which is a positive value, but the coordinate of point Q is negative, opposite of y above. So in this diagram, we see that the sine of theta in this diagram, it's the opposite of the sine of negative theta. They're not equal. And therefore, sine functions are odd functions. Suiting the definition of an odd function. In other words, we can write it this way: the sine of negative theta that was clockwise terminated in quadrant 4, it is the opposite of the sine of theta, which terminated in quadrant 1. Now, in terms of the cosine values, given theta, the cosine value is some positive value, right? X as a coordinate is positive in quadrant 1. And for the input negative theta, clockwise, that determines point Q, and the X value and the X coordinate is positive. It's the same as for point P. They're both X. They're equal. They are the same. In other words, we can express it this way, that the cosine of theta is the same as the cosine of negative theta. And that satisfies the definition of an even function above, up here. F of negative x is like f of negative theta, or cosine of negative theta, is the same value as the cosine of theta. So cosine functions are even functions. In general, the sine of negative theta, clockwise, is the opposite of the sine of theta, counterclockwise. And since the cosecant of theta is the reciprocal value of the sine of theta, similarly, cosecant of negative theta is the opposite of the cosecant of theta. And thus, also the cosecant function is an odd function. The cosine of negative theta, as explained, is the same as the cosine of theta counterclockwise. And since secant function is related to the cosine function, the secant of negative theta is going to be the same as the secant of theta, just like the cosine function. And thus the secant function also is an even function. The tangent of negative theta, let's think of this as the sine of negative theta, that's the input, divided by cosine of negative theta. Well, the sine of negative theta is the opposite of the sine of theta, and the cosine of negative theta is the same as the cosine of theta. Well, sine of theta divided by cosine theta is the tangent of theta, so we have a negative tan theta. Negative tangent of theta. And that suits the definition of an odd function. And since the cotangent function is related to the tangent function, they have reciprocal values, the cotangent function also is an odd function, and the cotangent of negative theta is the opposite of the cotangent of theta. Use these even and odd properties to find the exact value of the cosine of negative 60 degrees. Since cosine functions are even functions, the cosine of negative 60 degrees, that's the angle that is opening clockwise, it's going to be the same as the cosine of positive 60 degrees. And the cosine of 60 degrees is 1/2. Part B. Sine functions are odd functions. And so the sine of the input, negative 390 degrees, is going to be the opposite of the sine of positive 390 degrees. And if we break down 390 degrees as 360 plus 30, this will be the opposite or the negative of the sine of 30 degrees plus 360 degrees. Since the period of the sine function is 360 degrees and repeats every 360 degrees or every 2 pi radians. Thus, this is the negative of the sine of 30 degrees. And the sine of 30 degrees is 1/2. So final answer is negative 1/2. Part C. Tangent functions are odd functions. So the tangent of an argument or an input that has a negative angle is going to be the negative of the tangent of positive 37 quarters pi. Now, keep in mind that the fundamental period of the tangent function is pi radians. Its fundamental period is pi radians. So the tangent function value will repeat every pi radians, every 2 pi radians. And we can think of 37 quarters, which is an improper fraction, as a mixed number dividing 4 into 37. We have the negative of the tangent of 9 times 4 is 36. So 37 quarters is 9 1/4 times pi, or 9 1/4 pi. And then 9 1/4 pi, we can think of that as 1/4 pi. And that's a nice angle value because we can easily remember that for pi over 4, or 45 degrees, cosine and sine are the same value, square root of 2 over 2, so their ratio when you divide them will be 1. 9 1/4 pi is 1/4 pi, or pi over 4, plus 9 pi. Now, adding an angle of 9 pi is like adding 8 pi plus 1 more pi. And since the fundamental period is pi, adding 9 pi to an angle of pi over 4, the tangent function value will be the same as the tangent function value of tangent of pi over 4. So this will be the negative of the tangent of pi over 4, and then the function value will repeat after we add 9 pi radians, since the period is pi. And again, since pi over 4 has a tangent function value of 1, the final answer is negative 1.